Now we come to an additional class of reactions known as oxidation reduction reactions, or more commonly as redox reactions, where the RED comes from reduction and the OX comes from oxidation. Redox reactions are ones where electrons are actually transferred from one reactant to another. Previously, we hadn't seen that, but now we'll see actual cases where electrons move from one reactant to another reactant. And a classic example of this is the reaction between calcium metal and oxygen. So if we start with calcium metal here on a plate and just leave it out in the air, what we'll see over time is that it will be transformed into this white calcium oxide. So in this reaction, calcium goes from being the neutral metal to now being in an ionic compound. So it starts out neutral, but then it becomes the 2+ ion. Oxygen also starts out being as elemental oxygen, so it's neutral, and it ends up being the O2- or the oxide anion in an ionic compound. So in this process, calcium, since it started out neutral but ends up positively charged, it loses electrons. And the loss of electrons is referred to as oxidation. Oxygen, on the other hand, goes from neutral to being negatively charged, and so it has gained electrons. And gain of electrons is referred to as reduction. There's a useful memory device here for remembering oxidation and reduction. That's something that's known as oil rig, where oxidation is loss and the rig is reduction is gain. There are other memory devices for remembering oxidation and reduction, but this one is a very common one. So how do we know whether a substance has gained or lost electrons? And how do we know whether a redox reaction is occurring? Well, we can keep track of the electrons in a substance by using something that's known as oxidation state or oxidation number. And every element in a compound will have a unique oxidation state, its own oxidation state or oxidation number. And this number will change if the element has gained or lost electrons. And so this is what allows us to keep track of whether or not we're undergoing a redox reaction. So how do oxidation states work exactly? Well, there's some general rules that we follow to help us identify what the oxidation state for an individual element is at any given time. First off, any atom in its elemental form has an oxidation state of 0. So any of the metals, if it's just the plain metal solid, that's its elemental form, so its oxidation state is 0. Hydrogen, oxygen, nitrogen, those are diatomic gases, remember? So if they're in the diatomic form, then their oxidation state is 0. And kind of so on and so forth. Any element or any atom that's in its elemental form, the oxidation state for it is 0. So here's some examples, as I mentioned before. Even S8 is a unique elemental form of sulfur that involves a ring of 8 sulfur atoms. But in each of these cases, the element is in its truly elemental form. It's all by itself. It's not in a compound. It's not in a compound with other elements. So its oxidation state is 0. Second, for any monatomic ion, so any ion that is just composed of a single atom, the oxidation state is simply equal to the charge. So the potassium ion +1, it's just the single atom with a charge. That charge is equal to the oxidation state. So the potassium ion, its oxidation state is just +1, calcium's is +2, chloride is -1, the iron 3+, its oxidation state for iron in that case is just +3. Non-metals, with the exception of hydrogen, usually have negative oxidation states, which also matches with the charges that they would take in an ionic compound. So oxygen is usually -2. Hydrogen is +1 when it's bonded to nonmetals. It can be -1 when it's bonded to metals, but that's fairly rare. Most of the time we'll see it bonded to nonmetals. Hydrogen is +1. Fluorine is always -1, regardless. Fluorine always has a -1 oxidation state, and most of the halogens are normally -1 as well. One exception to this, the halogens are frequently an exception. Halogen oxidation states can be positive if they are bonded to oxygen, and the amount that they're positive will vary depending. And then the sum of the oxidation states of all of the atoms in a compound must equal the charge of the compound. So if it's a neutral compound, then the oxidation states must cancel each other out to get to 0. If it's a polyatomic ion like nitrate, the oxidation states, the sum of all of the oxidation states must equal the charge on the ion. So here, let's go through a few examples. Water, very simple example here. According to our rules, oxygen is usually -2, and hydrogen, when it's bonded to nonmetals, as it is in this case, is +1. So you look at that, there's 2 hydrogens, so there would be, on the plus side, there'd be +2, and there's 1 oxygen, so -2. Those two sum together, and we have a neutral molecule. The bicarbonate ion, or the hydrogen carbonate ion here, it has a negative overall charge, and we don't know right off the bat, none of our rules tell us what the charge on, what the oxidation state of carbon is. But we can deduce it because we know that oxygen is -2, and we know that hydrogen is +1. So if each of my oxygens is -2, that gives me a -6. I only have 1 hydrogen, that's +1, so now I'm down to -5. But my overall charge is only -1, which means that my carbon must be +4 in order to account for that. And that allows me to assign an oxidation state to each element. In this case, perchloric acid, it's a neutral compound. I know that hydrogen is going to be +1. Oxygen is going to be -2. Chlorine, though, this is one of my exceptions. The halogens can be positive and variable when they're bonded to oxygen. In this case, it is, and so it's going to be positive, but I don't know the amount. But I do know that the overall compound is neutral. If I have -2 for every oxygen, then on the minus side, I have -8 because there's 4 oxygens. I have +1 from hydrogen, so that gets me down to -7, but the overall compound is neutral. So the oxidation state of chlorine in this compound must be +7. Let's go through a few other problems and a few other examples. So hydrogen sulfide, the sulfate anion, elemental bromine, and this chromium anion here, this chromate anion. So if we take a look at each of these, in this first compound, hydrogen is bonded to a nonmetal sulfur. My rules only tell me about hydrogen, they don't tell me anything about sulfur, but I know that hydrogen sulfide is a neutral compound. So each hydrogen is +1, so that's +2. So sulfur must be -2. In the sulfate anion, I see that my overall charge is -2. Each oxygen is -2. And again, I don't know anything about sulfur in this particular compound, but I know that the sum of the oxidation states must equal the overall charge. So each oxygen is -2, that gives me -8. But my overall compound is only -2, so sulfur must be +6 in this particular case. And this is the oxidation state for that element. Now bromine, Br2 is the elemental form. So that's rule number 1, that the oxidation state for any element, any atom in its elemental form is 0. And then lastly, I've got this compound that's got 2 chromiums and 7 oxygens. I don't know anything about the oxidation state of chromium, but I do know about oxygen. Oxygen is always -2. So -2 times 7 is -14. I know that my overall compound is only -2, so that means I have to get +12 from somewhere. Well, if I have 2 chromiums, then +12 divided by 2 is going to be +6 on each chromium. And that's the process for how we would assign the oxidation state for any atom within any compound. Now, how does that help us in an actual reaction? How does that help us identify if we're doing a redox reaction? Let's take this example shown here. If I just track the oxidation states, I can see whether electrons have been transferred with a particular element simply by looking at the oxidation state on the reactant side for that element and the oxidation state on the product side for that element. So if I take this reaction between magnesium and hydrochloric acid, and if I just go through and assign the oxidation states at the beginning, so magnesium, it's just magnesium metal, that's the elemental form. Its oxidation state is 0. There's no charge associated with it or anything. In HCl, well, H is bonded to a nonmetal, so it's +1. Cl must be -1 in order to balance it and have a neutral compound. What I see on the product side, though, is that magnesium is now in an ionic compound. It's aqueous. If you break that up, you break it into the magnesium 2+ ion and 2 chloride Cl-1 anions. Since any monatomic ion, the oxidation state is the same as its charge, the magnesium 2+ now has a +2 oxidation state. So I've gone from 0 to +2, which means that magnesium has lost 2 electrons. Chlorine, it becomes 2 chloride anions, 2 Cl- ions, and so the charge is equal to the oxidation state. It's a monatomic ion. -1 is the same as what we started with, so nothing's happened with the chloride. Nothing has occurred with that. We would even consider this to be a spectator ion. However, hydrogen ends up now as H2. That's the elemental form of hydrogen, and so its oxidation state is now 0. And so we see that hydrogen went from +1 to 0. Now there's 2 of them involved, so each hydrogen gained only 1 electron, but there's 2 of them involved, and so the net gain of electrons was 2. And that matches with the net loss of electrons of 2 from magnesium. And that's very important. Whenever we have a redox reaction, the number of electrons gained, the total number of electrons lost must equal the total number of electrons gained. Those two things must balance each other because we can't lose electrons. That would violate our conservation of mass law, even though electrons have very little mass. So let's go through a couple other examples here. So we've got manganese reacting with lead nitrate to form manganese nitrate and lead. And in this case, manganese is in its elemental form to begin with, so it's 0. The lead, well, each nitrate ion in total is -1. There's 2 of them, so lead must be +2 as an ion. So monatomic ions, the charge is equal to the oxidation state, so lead is +2. Now within the nitrate anion, the nitrate anion is overall -1. Oxygen is always -2, so that would give me a -6, but I know that the overall anion is just -1, so nitrogen must be +5. On the product side, I can go through and see that nothing's changed with the nitrate ion as well. So nothing's changed with the oxidation state of nitrogen or oxygen. But manganese now would have a +2 charge, and lead is now uncharged in its elemental form. So we've gone from 0 to +2 for manganese. It's lost 2 electrons. It has been oxidized. Lead has gone from +2 to 0. It has gained 2 electrons. It has been reduced. Another example here, iron with nickel chloride. Very similar to the last one. Iron in its oxidation state is 0. Nickel in its oxidation state is 0. Chloride is -1, so nickel must be +2. Iron, chloride is still -1, so iron must be +2. So I've gone from 0 to +2. Iron has been oxidized, it has lost 2 electrons. Nickel has gone from +2 to 0. It has gained 2 electrons, it's been reduced. And what we'll see is that for many redox reactions follow this basic single exchange format, where we have some molecule in its elemental form plus an ionic compound, and then you essentially just swap out the two metals, and one now becomes part of the ionic compound and the other one becomes its elemental form. And that's very common for these type of redox reactions. And this particular form of a chemical equation is referred to as a displacement reaction, a single displacement reaction, because we've simply displaced the position of one group. So for all redox reactions, remember that both oxidation and reduction must occur because we must maintain balance of the electrons lost and the electrons gained. Okay, so how do we know whether or not a metal will be oxidized by an acid or by some aqueous salt? How do we know whether a redox reaction will occur? We can certainly track whether one has occurred by looking at the oxidation states, but how can we predict whether an oxidation or whether a redox reaction will occur? There's a very useful table that is referred to as the activity series of metals. And this activity series arranges all of the metals in order of their ease of oxidation. So if you are at the top of the table, these are the metals that are the most easily oxidized. And at the bottom are metals that are the least easily oxidized. The basic rule here, if you're trying to decide whether or not a metal will be oxidized by acid or by a particular salt, is that any metal can be oxidized by the ions of elements below it in the activity series. Let's go through an example of this. So copper reacting with silver ions. If I look in my table here and scroll down to find copper, copper is right here. And silver is below it, and it's the ions of silver. Any metal, copper, can be oxidized by the ions of elements below it. So the silver ions are below it in the table, so this reaction would occur. We would have a redox reaction occur in this case. I apologize, I think that, nope, I believe this is correct here in terms of the number of electrons that are transferred. We go from 0 oxidation state to +2, so we've lost 2 electrons. Silver goes from +1 to 0, so it only gains 1 electron, but there's 2 of them, so net we gain 2 electrons. Silver is reduced in this case. And if we show this in an actual test tube, we can see that this occurs. So we can predict it from the activity series, then we can go measure it in the lab. So if I take a solution of silver nitrate that has those silver ions, and I take a piece of copper wire and dip it in there, you will see now the formation of copper nitrate, which is that blue colored, so the copper ions forming in solution, and then we're forming kind of a gray film as we form solid silver. Another example here is a case where we have a metal and then an acid. So any acid, the ions that we're talking about are going to be the H+ ions, or the protons, and that's shown down here with the hydrogen highlighted in blue. So hydrogen ions, they will oxidize any metal that is above them in the series. So magnesium here reacting with some acid. If I find magnesium, it's up here, the metal, the ions, the H+ ions are below that, so this reaction will occur. And indeed, if we take magnesium metal and drop it into hydrochloric acid, we see rapid reaction to oxidize the magnesium and generate and reduce the hydrogen ions to hydrogen gas, which you then see as bubbles evolving from the reaction. So let's do just 2 more problems, and then we'll sort of finish this section on redox reactions. Will hydrobromic acid react with platinum metal? So it's an acid, so the ions that are present are H+. What we're looking for is the metal above the ions? Well, platinum metal is down here, all the way at the bottom, or near the bottom. That's below the ions. That reaction's not going to occur. If you take hydrogen and put it into a solution of hydrobromic acid, you won't oxidize the platinum because it's below it on the series. So that won't occur. But what about an aqueous solution of cobalt-2 sulfate? Will that oxidize aluminum metal? Well, what are the ions that are present? There's cobalt-2, that would be cobalt-2 plus ions. So let's find cobalt. Cobalt's here, so we're talking about the cobalt-2 plus ions. And then aluminum metal. Aluminum metal, that would be just aluminum solid, that's up here. So the aluminum metal is above the cobalt ions. So yes, this will occur. We would get, we would have a reaction between the cobalt ions and the aluminum metal to oxidize the aluminum metal and reduce the cobalt ions to cobalt metal. So this is the usefulness, the power of using oxidation states, of using the activity series to predict whether a redox reaction will occur, and then using oxidation states to keep track of the electrons in a reaction.